So here we're given an equation with trig functions, cosine and sine, and we're asked to solve this within some interval. So it looks like it's a quadratic expression, but instead of having x or y, we have cosine and sine. So we need to somehow link this variable to this variable so that we can turn it into a quadratic. So it's clearly some kind of a hidden or disguised quadratic. So we can make use of a identity that links sine and cosine, because we know that sine squared plus cosine squared gives us 1. So we can rearrange that to find sine squared in terms of cosine squared. So there I can replace sine squared with 1 minus cosine squared. So if I do that, I now have an expression that doesn't have any sine in it. It's cosine and cosine squared. And that's good because we're one step closer to writing it as a quadratic expression. So if you multiply by 2 and then you rearrange, so if you now rearrange this to make this positive, so let's move everything to the right. So move all these terms to the right. We end up with 2 cosine squared. 2 plus 5 is 7, so that's minus 7. And move that, you get plus 5 cosine. So now what we have is a disguised or a hidden quadratic. Even though it might not look quadratic, it is, because this squared is here. So if we called this variable x, then this would be x squared. So we can actually write that out. If we say let x equals cosine theta, we can now rewrite this with cosine and cosine squared replaced by x and x squared. Now it looks closer to what we recognize as our familiar quadratic. And you can use any convenient way to solve this. You can use the quadratic equation, or you can factorize. So I'm going to factorize it because I know that 2x squared is 2x times x, and negative 7 is plus 7 times negative 7. And if you check, 7x minus 2x gives me 5x, so that's correct. Now we've factorized it, we can say that either this is equal to 0 or this is equal to 0. And then we just solve to find x. So we have our two solutions, and that's the end of this quadratic. But it's not the end of our problem because we need to find theta, not x. So we need to replace x once again with cosine theta. So we're taking it back to the original variable. So even though x is minus 7 over 2, that means cosine theta is negative 7 over 2. And x is equal to 1, so that means cosine theta is equal to 1. Sorry. So what we want to do is to find theta. So we need to take the inverse cosine of both sides. So the inverse cosine here and the inverse cosine there. Now, negative 7 over 2, that's negative 3.5. That's less than negative 1, so there's no solution to that. So we can reject that side of the quadratic. So this cannot be solved, but this can. So the inverse cosine of 1 is 0. So that's our first solution. There's always a second solution for cosine. And the second solution is always 360 minus the first solution. So that gives us 360. So now we have two solutions, 0 and 360. And you can write this in this form. And that's your final answer. And you can always check. So if you go back to the original question, you can check by taking each of these values of theta and replacing it in the original expression. So sine 0 is 0, cosine 0 is 5, negative 5 plus 5 is 0. And the same for 360. You can replace 360 and you can check. Okay, so that's the final answer. Whenever you see a question like this, try to, if you have a cosine and a sine squared, replace the sine squared with 1 minus cosine squared, and vice versa. So what you want is always this and this to be the same, because written in this way, it's impossible to solve. So the only way, whenever you see a cosine and a sine together, is either to use tangent as sine over cosine, or to use this identity here.